Hey, everybody. We've got some very important stuff to talk about, so let's get right on into it. We're going to get into the structure of covalent compounds. Now, the structure of a covalent compound is as follows. Basically, the electronegativity difference is not strong enough for one element to take away an electron from another element. Okay, so what's going to end up happening is that one of those atoms is still going to be a little stronger than the other one, so they're going to end up sharing an electron. Okay, when two atoms share two electrons, then a covalent bond happens. Okay, it says the sharing that takes place can happen equally. Okay, that's if the electronegativity difference is less than 0.3. Okay, if it's less than 0.3, then that's considered an equal share. That's where both things feel like they have a pretty good hold on that electron. Or it can happen non-equally, and that's when one thing is much stronger. That's when one of your atoms is much stronger electronegativity wise than the other one. Okay, so if you have an electronegativity difference between 0.3 and 1.7, then that's going to be considered polar covalent. Okay, and so something that's polar covalent is going to have an unequal share, meaning that the electrons are going to be pulled towards one of the atoms. Okay, when it's equal, it's called nonpolar covalent, meaning that the electrons are pulled relatively equally. Okay, so a nonpolar covalent bond is where the electrons are shared relatively equally, and the delta En is less than 0.3. Okay, that's when we're looking at the electronegativity values differences. That's how we would determine that. Polar covalent, they are unequally shared, and they have a electronegativity value between 0.3 and 1.7. Okay, something else I need to mention is that we have what's called diatomic molecules. Okay, there are 7 diatomics that is really important for us to know for the rest of our lives. Okay, these are atoms that do not exist by themselves. Okay, they can only exist with either in a compound or in a pair. So I'll show you the method that I like to use for this. Some people use the I bring clay for our new house thing. I actually like to use a different method. I like to use the H7 method. Okay, and what the H7 method is a way that you can understand what our diatomics are. So the H stands for hydrogen. So hydrogen is one of our diatomics. The 7 comes from going to our 7th element, which is nitrogen, and making a big giant 7 on the periodic table until you get to a total of 7 elements. So I've got H, 7th element is nitrogen. So there's the second one. Then oxygen's the third one. Fluorine's the fourth one. Chlorine's the fifth one. Bromine's the sixth one. And iodine is the 7th one. So there's our H7 method. Okay, so that means hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are all considered to be diatomic molecules. Okay, so either way, that means that they can't exist by themselves. So if you're talking about hydrogen gas, it's got to be H2. If you're talking about bromine liquid, it's going to be Br2. Okay, iodine is always I2. So let's continue on here. So it says this is dealing with electronegativity. Now I know that based on my electronegativity chart, I know that oxygen is much more electronegative, 3.44, than hydrogen. Okay, so what that means to me is that oxygen is going to pull electrons towards it much easier than hydrogen is. Okay, so what that tells me is that my electrons are going to go in this direction much more efficiently. So if I'm going to show the pull of electrons for the bonds within F2 or HCl, okay, if I draw F2, it's going to look like this. So I've got a bond between my two fluorines. It's going to be relatively even on that because fluorine and fluorine are the same element, and so they're going to pull electrons in the same direction equally. So this would be a nonpolar element because all of the electrons do not move to one pole. However, with HCl, okay, I've got this situation here. When I go back to this, I've got the hydrogen's 2.1, chlorine's 3.16. So that's a very great difference between the two. So that tells me that my electrons are going to move, or at least are going to be pulled into this direction. So if I'm going to look at this atom, right, or this molecule right here, it wants to know how many polar bonds are there and how many nonpolar bonds are there. Well, all of my polar bonds are going to be bonds that I have between two elements of differing electronegativity values. So this would be a polar bond. So there's 1, 2, 3, 4, 5, and 6. So I've got 6 polar bonds there. There's one bond left, which is going to be my one nonpolar bond, and that's going to be my carbon to carbon bond. Since carbon and carbon are the same element, it's going to end up being a nonpolar bond. All right, we're going to take a look at how to draw Lewis dot structures for covalent compounds in the next video.